integrated water resources management. This is something that we are putting together. Various approaches are coming from the area of hydrology, hydraulics, climate, social, socio-economic kind of aspects of water resources management, and then trying to find a way how these tools can kind of communicate between them and how they can assist or provide the information for the decision makers. The second project mentioned in the introduction is a very large project where we are looking the coastal cities at risk. This project is an international project. We have 4 cities selected based on their location and the type of problems they may have under the changing climate conditions. So in Canada, we are looking Vancouver. We have Manila in Philippines, Bangkok in Thailand, and Lagos in Nigeria. And these 4 cities are all selected as coastal, very large coastal municipalities with very large rivers flowing through them. So the main hazards they're exposed to are related to sea level rise and potential flooding. So looking in the way how we can actually provide some adaptation or advice for the adaptation to the people who are living in these cities is really essential, considering the exposure and vulnerabilities and obviously the potential cost of changing conditions. I'm developing a spatial and temporal tool for modeling the resilience of the city, where various alternative options for adaptation can be kind of easily tested and through the simulation assessed from the point of view of increasing the resilience of the community. I am also working on the issues related to better understanding the climate science, looking into uncertainties. You know, we are all, if you're working in the area of water resources, we realize that the links between the climate and the humans are coming through water. And these links are, you know, to either change of the temperature or the precipitation, and then when the precipitation hits the ground, converts into the runoff flows, either you know, too much water or not enough water, and that's, you know, how we get affected by not having enough to drink or by being exposed to, you know, major floods, extremes, and of different nature. I'm also interested in using the systems approach to look at the broader questions, or the questions of a kind of, let's say, global interest. And in this particular effort, we are trying to model the link between the climate, water, food, energy, population. So basically look at how the water transfers the impact, the 2 drivers, the change in the climatic conditions and the change in the human population are affecting on overall kind of planet. So in this work, we are using the systems dynamic simulation. We developed 2 different models that can be informing the policy making related to, let's say, how to deal with the climate, mitigating the impacts of the emissions and so on. A little bit more focused work for the municipalities in Canada. We are developing the tool that is basically the working horse of every engineer within the municipality, so-called the intensity, duration, frequency curves, the type of tools that are used for the design of pipes or determining, you know, what type of flows or infrastructure we need. And simply lack of capacity within Canadian, at least, municipalities was really pushing very hard into this direction to provide and transfer some knowledge from our academic research into a practice through the modification or the procedure how to modify these curves under the changing climate. And we are developing this with the help of some National Center of Excellence. So the tool will be available on the web for every municipality to access with, you know, proper assistance and the sophistication which is in the background that will help the municipalities to do that. The moment when it becomes available on the web, it will be available basically for everyone who is interested in using it. And the last project currently under investigation is a very similar kind of idea of focusing on modeling resilience, but in this particular case I am working with the insurance industry. I didn't mention that, you know, my second hat is a very interesting entity. This institute is a very, I think, unique institute in Canada. It's established by the kind of integration of funds from the private industry, in this case insurance industry, Province of Ontario, which is similar to the state, that means provincial government, regional government, and the University of Western Ontario. So we have two offices. We have an office in Toronto, which is working very closely with our insurance partners, and we have a research office at the University of Western Ontario, where I'm serving as an engineering chair, and we have another person who is serving as a policy chair. And we do research that has some value to private industry as well as, satisfy the needs of the society through the kind of public type of research work that we are doing by funds provided from different sources. This one is supported by the very large reinsurance company, Montpellier Reinsurance. They are situated in a very beautiful place in Bermuda, so Tanya and I have the opportunity to visit them during the winter time in Canada. Let me now move into my lecture. What I would like to talk today is basically related to what is presented in this publication and dealing with the systems approach and how the system approach relates to disaster management, and what is in this publication and deals with a kind of risk management. So there are two key messages that I would like to send through the presentation, and I usually like to start my lectures with conclusions for those of you who may rest during the rest of the presentation. I'm seeing disaster management as a very, very serious problem, and a problem which is facing the increase in complexity. There are, in this particular domain, very intensive interactions between three different subsystems: physical kind of system, human, and the constructed system. So these kind of interactions are the main source of the complexity, as well as basically they convert the hazards into what we call disasters. And I'll try later on to provide at least my definitions of that. In response to this particular kind of fact and the need that we are facing many and more complex and more devastating disasters, I would like to offer as a potential solution systems approach, or the systems view of that particular problem, as a really different way of looking the disaster management problem. This is where we are kind of focusing on the broader picture, where you are trying to identify what are the kind of key components that make a disaster, how these components interact, how they affect each other. And only when we kind of achieve that level of understanding, apply the proper tools that may help us, find the solutions. Systems approach offers different ways of dealing with problems. You can either identify the optimal solution, the single optimal solution that will give you the best possible design, the dike of the particular height that will provide the best protection from the flooding. Or the systems approach can give you the understanding how is the system behavior changing under the longer term changing broader conditions. So that you don't have the single kind of answer, but you get the insight into understanding, what is causing the change within the system, how is this change occurring, and then possibly think about the solutions that may change that in the direction that's more acceptable to the society. And the final point of the presentation and the conclusion is that risk assessment and management are, at least in my work, now being seen as the response to this complexity challenge, but also as the way how we are going to adapt to changing conditions in the future. The level of uncertainty being introduced by the changes in the natural as well as the kind of socioeconomic and built environments are so high that we will not be able to eliminate the risk of the kind of natural disasters in the future, or the impact of natural disasters in the future. So if you are not able to eliminate the risk, what I am trying to say is we have to understand the risk and try to assess the risk up to the level that we can find the solutions that will be kind of minimizing that risk. So through assessment, through proper ways of understanding what is causing the risk, we will be able possibly to arrive at some adaptation options that will reduce the risk. I'm going to provide you with some examples at the end of the presentation, and you will see one example in the real setting of the city of London where we live, how management of risk may be an answer for the more serious problems. I'm also trying within this particular research domain to send another message that risk is a mix of the objective and or the consequence of the mix of the objective and subjective uncertainties. And what is interesting, objective uncertainties are something that we should be really paying attention to. Objective uncertainties are, high water, not enough water, something that can kill the people or create damage. However, we all as individuals perceive these risks in a very different way. And it's mostly driven by our experience, or it's driven by our own value systems. And now if you look at, so we are somehow creating a picture of the risk that's not directly related to objective characteristics of risk. And being in, or living in a democratic societies, we are under this kind of subjective impressions actually implementing them in everyday life, and basically we drive the decisions mostly on the basis of that subjective or perceived risk, which is a product of the individual value systems. We elect officials, we talk to them, and when we elect the officials, this is all based on the way how we see the policies of the proposed policies of the officials, possibly affecting risk. Again, I have an example that I'll try to illustrate that message. I think this is a pretty important message because of that discrepancy between the objective and subjective uncertainty and our very traditional way of focusing in finding solutions by only considering objective risks and ignoring what and how the people react and what the people think and how to actually take the value systems of individuals in that process. So I've seen this, I really like this picture. I have one more video, but I decided not to show of the landslide, and it's amazing video how somebody avoided being killed in that. This is known to all of you, the Typhoon Morakot and the impact that this particular typhoon had on the Taiwanese society in the sense of material damage and the number of lives lost. And what is more interesting, what was coming after the typhoon and how your political system changed and impact on the government and the change of premier and so on. So I think it's an excellent illustration how these natural disasters do actually affect almost every aspect of life, and how this cannot be only seen as a engineering or as a technical problem. It has to be looked at in a different ways. I'll try to go through the presentation by talking a little bit about the kind of setup. You already, I think, got some of the ideas that I am trying to convey. And then through the introduction, kind of illustrate the requirements and challenges of the integrated disaster management, and then I'll focus, for a very brief period of time on systems analysis and what the systems analysis can offer, risk management, what the risk management can offer, and I selected 4 different examples which are basically supporting, I think, the need for the use of the systems approach and risk management if we are going to look at the disasters in this integrated way. So this is the kind of key, I think, setup that we are talking about when we are mentioning natural disasters today. You have this interaction where the humans are obviously in the middle, and the impact that is, the people may experience through the impact of the disaster. We have a changing kind of physical conditions. This is the, I think, picture of Morocco 2. And we have this built infrastructure that's being affected. We have roads, we have bridges, we have buildings. They may be on the way, high waters, that they may be affected. This is, the type of disruption that easily get, and affect the people. You have a road that is kind of affected by the flood, that prevents, emergency services to be provided to people. It cuts some people. It prevents people from being evacuated, and so on. And I think this kind of setup exists in any kind of disaster. And I learned through the interactions during my stay here how serious, focus is in Taiwan on earthquakes, typhoons, flooding, landslides, debris flows, and so on. And I think everything, all these kind of aspects are very much the same for all these different types of disasters. So in this kind of changing conditions, I think we are starting to face very changing environment for understanding, defining, and approaching natural disasters. We are in the stage where the climate is being kind of altered. We are seeing the major changes in the land use, land productivity. We are observing the changes in the oceans and the freshwater resources, atmospheric chemistry, ecological systems, and that's all kind of directly or indirectly affecting or links to natural disasters. Understanding and predicting the causes and impacts is really the focus, I think, of our research, and I think your whole academia and many of the programs that I have seen at universities are focusing on that, on increasing our knowledge and understanding the long-term climate change and greenhouse warming impact, how the atmosphere is, radiation is changing, what the natural fluctuations and seasonal and interannual time fluctuations are doing, and how that gets together, or how that impacts the extremes together with the longer term change, like climatic change. So the point is that almost everything that's occurring around us is kind of directly related to natural disasters, and therefore I think there is a need to look at their management in a different way. This is a very traditional way of looking at disaster. This is called the kind of disaster management circle, except that I replaced the circle with the so-called Moore diagram, where you see these overlaps between the four major sets of activities, from kind of preparedness to response, recovery, through mitigation. And what I'm trying to say is that we are not going from one to another and then to another. This is a number of, I think, when we are talking and managing natural disasters nowadays, we're talking about set of actions and activities that kind of overlap and cover, some aspects of the preparedness as well as mitigation or response. So this is the kind of little bit different graphical presentation, and I think that's the reason for this kind of little bit different name, that I am looking at the disasters in a kind of integrated ways and management of disasters in this particular set. So in kind of, if you accept this difference, it is a really minor difference. The disaster management process becomes an iterative kind of process, and it is a decision-making process that kind of affects almost every of these four steps, but also through the kind of iterations and the modifications in one of them, we may affect and change some activities in those that are kind of overlapping with. So this is all happening in the same time when the kind of societal attitude is majorly changing. We are seeing, very serious concern about kind of social issues. The economic issues are still becoming and remaining very important. You are going to see some of the messages that I was able to kind of generate through the research, and also the concerns about the environment. So we are seeing the way how we function as individuals and organizations within the society, which are directly kind of affecting, I think, management of disasters, and I think contributing to this integrated idea of managing disasters. I don't think that most of you need this. This is a very traditional kind of list of what the prevention, protection, preparedness, emergency response, and recovery kind of include. It is important to know that this is kind of being implemented in different countries, in different societies in a different way. And I was really happy to learn how is Taiwan kind of looking at that and compare that with my experience and knowledge from Canada, where we have a completely different way of managing natural disasters. But the point is that in each of these kind of steps of managing disasters, we are focusing on different things, and some of them may kind of belong to two or three of these different categories. The other aspects that are kind of creating requirements for different management of disasters are that we are seeing larger and more frequent disasters. Every lecture that, or the presentation that I participated at different universities and NCDR started with some graph or some piece of information telling me that in Taiwan you are already observing, much more frequent and kind of larger disasters in all these different 5 kind of categories. And I think the similar message is coming from many other places around the world. This morning I was communicating with a colleague and friend from India who was telling me that in the city where he lives, for the first time during the month of April, they already experienced 42 degrees Celsius. And we were talking to our kids back in Canada, where the local weather, exceeded all the historical minimums. We had the longest, the coolest winter with the most snow. So this kind of extremes that are popping up at the different places and different kind of locations are, I think, indication that something is changing. This is bringing, the increase in the kind of complexity and how to deal with that. We are simply not fully, we're not fully prepared. I mean, if you have a situation like plus 50 degrees in Sao Paulo, I have a postdoc who is from there, and they depend on the water supply that is being fed by the rainfall during the spring, and they didn't have a drop of rain. That means very serious questions and issues for the population of 22 million people living in that very large urban environment. So that's where, this kind of new changing conditions are now asking for the new solutions and new ideas. In this domain, the focus that was in the past mostly to understand the physical or the changes within the physical system, understanding better the hazards, predicting the hazards with a high level of accuracy and so on, is really changing. We are moving into trying to understand the disaster risk. We are trying to manage the disaster risk. It is not sufficient anymore to only focus and increase our understanding of the hazards. I am repeating here this particular set of requirements that are coming from the fact that disaster management is the interaction between natural, social, or human population and built environment. So if this is the case, we have to have ability and tools to fully understand how these 3 subsystems are interacting. And as the title of your center is saying, this whole setup is now within the very important, I think, context of trying to find a way how we can sustain the life and the world around us. So the sustainability, I would, kind of sustainable development is being seen as a paradigm introduced after the UN report published some time ago. But basically, it's a kind of moving goal, and it's something that we all strive to. But the way how we deal with that is through the change of the kind of objectives, procedural policies, and implementation. So that's what is also coming back to the disaster risk management, and together with a kind of change in the technology and basically very fast change in the technology may contribute or creates a set of requirements that new disaster management approaches should meet. So the challenges are coming from the fact that people, infrastructure systems, both hard and soft, are changing. We have a tremendous population growth. We have a growth of the urban populations. 80% of the world population is now, is predicted to be in urban environments very soon. We have migrations. Right now, the UN is focusing, for example, on the climate migration, where the people from the places where the climate is not conducive anymore to provide enough are moving to other places where they can have food, water, and support life. So these are the things that didn't exist before, and may create very changing kind of social conditions in the places where the life or the support for life may be a bit better. On the infrastructure side, we are changing the hard infrastructure, because we need water, we need energy, transport, communications. We build the roads, pipes, bridges, and our life depends on the existence of this physical infrastructure, and the physical infrastructure then becomes affected by the hazards that may exist in the region, and that's how easily disasters are or can be created. The soft infrastructure is also playing a very important role, because this is defining how we respond to these challenges. The institutions, how are the institutions organized? We have industrial, social, cultural aspects, and they all play the role in different steps or in different points during, before, or after the disasters. It is very interesting that we have a very reactive type of response to natural disasters in almost every country. And there is a so-called window of opportunity that usually follows some big disaster event, that gives us opportunity to do something and prepare ourselves better for the future. But kind of having a proactive and permanent focus on the disasters is not, I think, visible almost anywhere around the planet. And the reason is the cost is very high, and our politicians do have a very short kind of term or objectives that are short term, basically to be re-elected, and we have a period of 4 years, which is a common kind of period. So you realize that the longer term changes, like changes in the climate or something like that, do not come under their lens. Globalization is another challenge, because now we have contacts and communications. The supply chains or the economic activities are now so linking us together. When Fukushima accident occurred and the big earthquake occurred in Japan, we lived 60 kilometers for a very small city of Woodstock in Canada that has a very large Toyota plant. And almost all the population of the city is employed by the plant, and the plant was not able to function for 3 weeks after the disasters because the parts were not coming from Japan. So you see, the disaster, natural disaster on the other side of the world, basically affecting the people and the economy in a completely other location. So that's the consequence of this kind of globalization, and this is how I think disasters may be affecting us together. On the challenging side, the climate, I would like to give this a little bit more attention. The climate change is really being seen as one of the very serious challenges. The climate is mostly manifested in the change of the frequency and magnitudes of extreme events. And IPCC, Intergovernmental Panel on Climate Change, is not very strong in wording and linking the change in extremes to natural disasters. The danger is, linking particular single event to a long-term change in the climate conditions. But the facts are that we are observing more frequent hot days, hot nights, heat waves, heavy precipitation events, intense and longer droughts, increase in tropical cyclones, increase in the sea level, and so on. So these observations are already in place, and they are very clearly sending the message that something is changing. Do we want to attribute everything to the changing climatic conditions? is, I don't think it's of primary concern, but it's important to realize that the changing physical or changing conditions within the physical system are generating these feedbacks, and I think everything is basically about feedbacks that affect the society, people, building infrastructure, and so on. So it is all about the feedbacks, and I think we have proofs already that climate change is much more serious than expected. We see that through the temperature increase, concentration of greenhouse gases, sea level rise, and melt of the sea ice, as well as the glaciers. So the manifestation of the climate change enters into the hydrologic cycle, almost every aspect of the hydrologic cycle. Precipitation patterns, intensity of the precipitation, snow melt, infiltration, evaporation, evapotranspiration. Almost every aspect of the hydrologic cycle is affected by the changing climatic conditions. And that is, kind of propagating into the natural disasters, or at least disasters, the climate related. So earthquakes are not in this particular category, but almost everything else that's of concern in Taiwan, typhoons, floods, landslides, and debris flows are kind of related to the climate and changing climatic conditions. And this is where I think understanding these feedbacks and trying to do something to affect the changing conditions is the possibility for reintroducing the systems analysis. This is my favorite definition of the feedback. And the feedback theoretically is basically the change of the system that produce some action that back changes the system. I'm using, when I teach, the thermostat is a perfect example of the mechanism that controls the temperature in the room. The temperature in the room is the description of the state of the system. If you want it to be lower, we set the temperature on the thermostat, and this is measuring the state of the system. If the temperature goes above the desired, activates the air conditioning. Air conditioning brings the cool air into the room and reduces or changes the state of the system temperature. So that's it. What I'm trying to show with this cartoon is that we are also now somewhere in this process. These poor guys representing all of us, I would say, and the process is kind of going on. The question is, how fast is this going to come here? Is this last domino going to fall down? Are we going to be able to kind of slow that down? Are we going to be able to move left or right? Or, what will happen, if these feedbacks start dominating and creating the conditions that will not be anymore supportive of life? This is just, a few illustrations. This is the picture of 1959 in red of the Arctic ice cover, spring ice cover, and this is 79, and this is 2005. And the difference in the area is 35%. So this is kind of one indication that something is happening in the Arctic, that we are losing this white area, we are losing ice, and that has multiple consequences. More water entering the oceans, the darker areas absorbing more energy from the sun, and the process kind of continuing of the increase in the temperature and so on. So we have this kind of interaction between the natural systems that are causing the climate change and our response, or the social adaptation, and that is a very large kind of scale feedback relationship that drives many activities within that kind of circle. So interaction between the physical or the climate change and the social systems or the social adaptation determines the entire state of the system and the evolution of the system, and that's what is, I think, putting us into the middle of this question of the climate change and the potential impacts of climate change. There are already feedbacks in place in work. Some of them are smaller, but very strong positive feedbacks, and some of them are pretty dangerous, and they are kind of starting to slowly come up. the success in dealing with the questions related or impacts of climate change will be basically the question of our ability to deal with these feedbacks and somehow affect them. Positive feedbacks are something that we don't like. Positive feedbacks are destabilizing the system. They are pushing the system, from the stable state. Negative, the thermostat is an example of the negative feedback, where basically the instrument is controlling the temperature and trying to stabilize the system at the desired level. So almost all the feedbacks that are occurring in the nature right now are on the positive side. So they are very much destabilizing the system. We have an example: the higher temperature, global temperature, is warming the ocean water. That increases the evaporation. Water vapor is very potent greenhouse gas that kind of increase the concentration of the greenhouse gas, and this further continue trapping the energy and increasing the temperature. So you see how, this positive feedback may continue contributing to warming. Similarly, with the melt of the snow and ice, losing the white areas and basically increasing the absorption of the sunlight will continue the process of losing more snow and ice and therefore increase the temperature. The more dangerous feedbacks are the feedbacks that may have a relatively high inertia, and if these processes are being activated, we will have a very hard time finding the base of controlling or stopping these positive feedbacks. The two most probably dangerous are the melt of the basically permafrost. Northern Canada, northern Russia contain very large areas of the frozen ground, and within this frozen ground we have many organic matters, and basically the methane gas, which is a consequence of the decomposition of the organic matter, being basically kept within this frozen land. So with the melt, this methane is being slowly released. And methane is about 22 times more potent greenhouse gas than the CO2. So the smaller concentration of that gas can contribute to a much faster change in the temperature. And they're already documented facts. The permafrost in northern Canada is, it's seriously melting. We have, for example, serious issues with the foundation of the smaller communities in the north. We have a serious issue with so-called the northern roads, which are relying on the frozen ground in order to provide for the transportation. The kids in the north, I didn't see that, but I participated in a presentation and I've seen the pictures. The kids in the north are playing by approaching the puddles and lighting the fire. Each puddle basically is a melted ground, so the methane is coming out, so it becomes like a small fire that kind of permanently lights the north in Canada. And this is kind of happening they're saying, on a very wide basis there. The second important big and dangerous feedback is movement of the climate zones. Change of the vegetation and change of the kind of species distribution is the process that is occurring very slow and can completely change the way, how the environment and the species are obviously using and interacting. This is a very sad picture because this poor bear was killed in the Canadian North, but this bear is something very, very rare, and they're saying not anymore so much. Look at the face. This is the bear that has actually the mix of the polar bear and the grizzly bear in it. And they did a DNA analysis of this poor guy, and the DNA analysis showed that that was already second generation mix between the grizzly and the polar bear. And these two species never lived together. That they were very, being separated by the climate, and now by the changing conditions, you have a situation like this where they start kind of populating the same areas and started kind of mixing. And this is, these are kind of anecdotal fact. You cannot say, based on this, that the change is global and happening everywhere. But I think they are very much supporting what the kind of science and the physical science is providing us with through the observations and the development of tools and techniques to understand what observations are saying. So I would like now to move into my kind of messages, at least the first one. Let me just have a little bit of water. I forgot to mention, I don't mind being interrupted. If anyone has a question, raise your hand and I'll, choose the moment and try to address it. We don't have to wait until the end. So feel free to ask questions. So the first message of, the work that I'm doing, and especially the kind of approach that I'm trying to develop, is that we, in looking at the disasters, and especially management of natural disasters, we have to change the view. And this particular view, I think, can benefit from the systems analysis, systems approach, and systems thinking. But we also have to look at the disasters as a very specific type of system. And I'm saying is that the appropriate way of looking at it will be to consider this as a social system. And I think I mentioned in one of my lectures, I don't know if somebody already heard it, I'm repeating myself, but I'm an engineer. I'm training, future engineers and educating them. And when I say that, we should be looking at the systems we are working in as a social systems, my colleagues are not feeling very happy about that. And I was making a presentation in Stockholm in one very large meeting where I was elaborating on this idea. And there was a colleague in the audience from Denmark who stood up. I was saying that, actually I was talking at that time about the water resources and water resource management. He said we should be looking at the water resources systems, the social systems. He stood up, said, "You don't know what you're talking about," and he left the room. He didn't give me a chance to answer and provide my argument. He was so unhappy with that statement that prompted him to basically leave the lecture. But I strong very, my position is very strong behind it, that the systems we are talking about are the systems that contain these elements, individuals, organizations, societies, and we are all embedded in the environment. And there are two types of flows of resources and information that are basically determining the state of the systems and also how they change. So by basically using the understanding the flow of resources, this is easier for us. We can determine the state of the, let's say, environment. We can measure the water quality. We can determine how much water we have in the watershed by doing some hydrologic analysis and so on. But how you convey that information on the, to, let's say, an organization that's responsible for managing the water resources in order to secure the water supply for the city of Sao Paulo is very different. And it's very much driven by our kind of values and use of this information. What is the meaning of the 220 millimeters in 2 hours of precipitation to you or me is very different. It depends on our kind of exposure, our experience, and that's where I think this kind of social aspect of the system that we are dealing with is coming into the picture. So values are providing the meaning to information flows, and by providing the meaning to information flows are basically affecting the whole process of managing these complex systems. In the textbook, I kind of focused on mostly technical side, how the systems approach and what are the tools and techniques of the systems approach that can be of value for managing disasters. And there is a whole kind of theory and lots of information on different tools, from simulation to optimization, multi-objective analysis, indeterministic and stochastic environments, and so on. I have some preferences, and these preferences are mostly related to kind of personal experience and the long-term involvement with different techniques and different settings. But I'll kind of give you some examples that illustrate that. So using this text, you may learn about tools and techniques, but what I'm talking about is the application, and where is the value of this approach and how these particular tools can help us to deal with the more complex systems. The second message is related to risk. In the book, I'm defining the kind of disasters as the situation when hazard triggers vulnerability and disruption of the functioning of a community or a society that exceeds the kind of ability of the community to kind of cope using its own resources. So there is obviously that side of the hazard, what is affecting the community, and there is that side of the vulnerability or the exposure that both play equal importance in the definition of risk. But there is something that we as kind of individuals have in our mind. Explicitly, we consider the impact of hazards in our understanding of hazard. We are implicitly considering the damage or kind of that negative impact that the hazards have. So therefore, the disaster risk is usually our interpretation of the negative economic and social consequences. And because it's our interpretation, it's automatically kind of subject to our judgment and the value systems. And that is, I think, providing a little bit stronger support for my idea that we should use and we should focus on these as the social systems when we are trying to deal with them. In the book, I'm defining the risk as the probability of the of harmful consequences or expected losses resulting from the interaction between the hazard and exposure or vulnerability. So very simple formula that these two components are equally contributing to definition of risk. When I was a student, both undergraduate and graduate, I was taught that risk is nothing else than basically hazard. And that's what we were doing, trying to understand what the wind does on the building, what the amount of what is the amount of flow that will be overflowing the banks of the river, and that was our definition of understanding risk. This is a very kind of different setup now, and it brings a lot of different kind of issues into our consideration. So we have to take into consideration this global change. We have to take into consideration the uncertainties that are coming from both sides. And I would like once more to stress the importance of this fact between the difference between the objective and subjective uncertainty.
I'm sorry, can you please?
I'm so happy that you decided to ask me questions.
Thank you, this is great. Can you please go back to your previous slide? I would like to learn more a little bit your interpretation about vulnerability in this equation.
Okay. I'll be actually what I am now talking about is the vulnerability. Basically, the vulnerability defines the exposure or the impact of the hazard. It may have multiple dimensions, and we may look at that in a very different ways. You can focus only on the kind of social or economic or health, or you can look at that kind of together. So in the example that I'm planning to show later, I'll be kind of providing some further input into that. The kind of, I think, concluding message here is that if we are considering risk as pointed out through this relatively simple relationship, but the relationship that kind of brings hazard together with the vulnerability, then management of the risk is becoming a very powerful tool for adapting to changing conditions. So by managing the risk, now we can kind of find in both areas hazards as well as the vulnerabilities that we can intervene in order to kind of reduce the risk. That also expands the domain of action in a way with the kind of natural side or the hazard side. We can do something that will change, let's say, the concentration of the greenhouse gases that may be contributing to changing climatic conditions, precipitation, and so on. In changing the vulnerability side or the impact side, we can do a lot to provide a high level of protection for people, evacuate people on time, minimize the potential damage, decide, for example, what type of criteria we will be using in distributing the funds between, let's say, health services and transportation or something like that. So I think by looking this broader formula is giving us now more opportunities to devise the adaptation options or measures that may reduce the risk more effectively. And that's why I'm now saying kind of management of that risk is now becoming a very powerful tool for adaptation to changing conditions. There are a little bit of the theory. The risk can be multidimensional, measuring, resilience, reliability, robustness. There are all kinds of different ways of looking at the risk or looking at risk in a more complex way. How often the system fails, how fast the system recovers, that's resilience, or how capable is the system to function with a lower capacity, that means robustness, and so on. The finding ability to bring both of these objective and subjective together into the process of management is also very, very important. And I think the researcher that was doing contributed to that a little bit with the introduction of the fuzzy set theory that was not very common in engineering in the past. So this book is providing now the tons of different tools in both probabilistic and fuzzy environments. And you see in both books I was focusing on presenting the techniques and presenting the tools. And I did illustrate how the different tools and techniques with a number of different examples. But what I'm now talking about is that setup where I hope you all will be able to learn or use or find out how some of these different tools may be helping with the problems that you may be dealing with now or in the future. Again, I have certain preferences, in the use of these tools and techniques based on my kind of experience in the simulation area, in the optimization, and I'll give you also some examples so you can see how this was used. So this is kind of, I think, sufficiently long to put you to sleep on what the disaster management, natural disaster management is, what are the kind of points that I wanted to convey through the potential benefits of systems approach and risk management. And now I selected the kind of 4 examples that may be a little bit more interesting to just kind of go and illustrate some of these points with a little bit more concrete type of work. The first example is in the use of the systems approach, and particularly system dynamic simulation. For some of you may be not familiar with the technique, this is the way how we actually try to describe the structure of the system, and by describing the structure of the system through the process of simulation, analyze the behavior of that system in response to different inputs. We can either change the input values into the system, or we can change the structure and observe how that will affect the system behavior. So these models are very powerful. They are not predictive models. These are not the models that will give you the exact value, but they will be able to show you very nicely, the character of change of the particular state variables, and provide a little bit more insight in understanding how we can relate particular structure to a particular type of behavior. And in 1997, we lived in central Canada, province of Manitoba, and I was teaching at the University of Manitoba, and we experienced the flood of the century. The Manitoba is the location where the Red River, which comes from the United States, flows into Canada. One of the 9 rivers flows north, and very large watershed, 165,000 square kilometers, like about 5 Taiwans altogether, and 85% of the watershed in the United States, and 90% of the basically population and the damage in Canadian part of the watershed. So what is happening when the flood occurs in this particular area, large amount of snow melt and water comes north. The conditions are prone for flooding because the north is still cold and you don't have a clear flow for the water, and the water starts spreading over the large area. The 1997 flood created a lake of 2,700 square kilometer large. I had the opportunity to fly with a colleague of mine in a small plane We were flying from the city of Winnipeg, which is in Canadian part, 80 kilometers north from the U.S. border, to the U.S. border, and because the altitude was controlled by military at that time, from the altitude we were given, we were not able to see anything except water. Anywhere, front, back, left, right, just, you know, huge, huge lake. This particular flood moved about 38,000 people, involved all levels of government, and a very intensive communication and collaboration with the colleagues from the United States. I was one of the 5 Canadians appointed by the Canadian Foreign Minister and U.S. Minister to work on the so-called International Joint Commission that provided, we were given $7 million and terms of reference to provide advice to both governments how to deal with the floods of this nature or larger in the watershed. And it was very, very interesting experience. In my professional life, I think I learned most from that experience than from anything else. I can teach you how to build a dike very easily, but how to go through something like this as a person, as a family, as a member of the community, and how to deal with the stress from the beginning, understanding what's coming, to protecting yourself, to recovering after the disaster is something that nobody can teach you except the experience. So one of the very serious problems was the problem of evacuation. 38,000, I'm talking only about the Canadian part, 38,000 people needed to be evacuated, and many of them were objecting that. The main reason for objection was that people felt if they do not protect their own property, if they don't run the pumps, if they don't build temporary dikes around their homes, the homes will be flooded. Many of them lost homes, lost everything. And in Canada, there are very specific and very strict rules that the human life is the first priority. So if the evacuation is called, you have to move. If you don't move, they send the police, they put you on a bus and take you out. And that was not well accepted by the people. And what we have done is, after the flood, based on the information and experience, we decided to build a tool to help emergency managers maybe deal with this evacuation process in a little bit better and more efficient way. So this is how we looked at the whole process of evacuation, from the floods coming into the region to the concern being raised by the people, recognition of the danger, acceptance of that, and acceptance of the evacuation decision so that we can finally reach the safety. And you see that in this process, we considered tons of different kind of factors. SF stands for the social factors, external factors, initial conditions, psychological factors. So we tried to actually integrate now how the people react, what they perceive, what are the real physical conditions, like initial condition, what's coming, what is the flow, what is the expected elevation, and so on. And how this process of kind of receiving the information to reaching the final safe destination is affected by these different factors. And we built a model of that. So what was the purpose of the model? This was the work conducted for our emergency preparedness services, and mostly for training the emergency personnel on finding the best ways to communicate the flood warning and evacuation orders. And these were the kind of typical options, at least in Canadian setups: use of the mail, radio, web, TV, and so on, use of the mail to provide evacuation orders, or the direct visits. Also, we identified some of the key social variables, the behavioral variables that were playing a very important role. And all of this was done for that particular setup, Red River. We were lucky that after the flood, we had opportunity to involve a group of social scientists to go out into the valley, talk to the people who were evacuated, and collect a lot of information that actually provided the background for the development of the model. So we were looking into timing, we were looking into some issues like the coherence of the community, for which I learned for the first time how important that can be during the flooding. We have a lot of Mennonite communities in that particular region, and they are working really very closely together. If you tell them, you know, go there, start building something, they all go there, they start building something. On the other side, we have different types of communities where no one talks to each other. And their response was much slower and much, you know, creating much more difficult situation for dealing with that. So this all information was integrated and put together into a type of model that was able to basically allow, now this is like a game where you can select, you know, the type of order and the warning, you can select the characteristics of this community, and then the model simulates how fast, or this is time, this is the number of families being moved from one place to another. Model simulates how fast they reach the safety. So now we were able to allow, through the use of this kind of simulation tool, to help them understand a little bit better the local conditions and the response of the local people, and basically also understand that there is, you know, your lack of understanding may create serious consequences. You see the difference where the people can be kind of evacuated within the 48 hours, and in some conditions, you know, it will take much longer. So your understanding and knowledge about the community, the way how they react to these different messages and different ways of communicating the message is playing very important role in the efficiency of the evacuation process. And it was a very interesting, I'm now telling you the stories, I don't know how much time I have, but when we were going into the community and we were asking, you know, what would be the best way to communicate the information about evacuation here? And can anyone guess what was out of these potential options was the response? These were the options. These were the options. What do you think? Just tell me. So the answer was, majority was the web. So I was thinking, my God, okay, so there is a large flood coming, huge amount of water coming towards me, and I'm sitting at home and checking the web, you know, to find out. I don't know, I was surprised, I must say. But it seems that people were receiving it. We are talking now 1997, this is not today. Today probably Twitter or, you know, Facebook or something like that. But the point is that, you know, you have a very different kind of behavior that's obviously consequence of the available technology and the way how the people are now changing receiving information. So this was an interesting example, a relatively you know, simple tool, but of tremendous help to potentially prepare the personnel, emergency personnel for the future evacuations in the area.
Sorry, can I learn something more about the different patterns of lines in the diagram?
They're just showing this lines are showing the same thing, but a different scenario. Okay, so this is the time, and this is the number of families. Okay, so this tells you if we have a scenario one, and the scenario one is the combination of the particular warning and particular evacuation order and particular setup of the variables of the community. So if you change them, you get a different response, and you see, you know, much faster response. And so the point was that different combination of these factors are increasing or decreasing the efficiency of the evacuation. And that's what we try to learn. So, like, if you're interested to use this in Taiwan, it will not be appropriate, because we captured within the tool only the community and the response and the characteristics of the community over there. But with the small modifications and the similar work, bringing the characteristics of the local communities here, you can have, you know, very similar tools.
You have to do all this before the flood?
No. This was all done after. This was all done after the flood, and the purpose was we were actually hired by the emergency management organization to provide this as a really training tool for their personnel.
Oh, okay.
So they can learn, you know, how to handle the situations a little bit better, because it was a tremendous reaction, Everyone was unhappy. We lost the province lost the premier because of that flood. He came out and said that, you know, people should take personal responsibility, and he was not elected after that. Okay, but this is the story about the Canadian political landscape, and I don't have time for that. To tell you now, so this was an example of the systems analysis based on a simulation. So where over time you predict the change of the system. So it's not the point in the tool like this. It's not the point of exactly, you know, what will be the time for 30 families or so many families to move. It's the point of understanding that there is a difference between a set of options that generate this type of response and this type of response. So you can learn how the system kind of responds to changing conditions, and that's what the benefit of the system dynamic simulation is. The other application of systems analysis is through much more, I would say, focused type of tools, mathematical tools that are trying to find a single solution that either minimizes or maximizes some objectives. In the single objective context, we have a mathematical function that can measure, let's say, the benefits from the particular action or the cost of the pipe of the particular dimension. This objective is subject to a set of constraints that you have to pass the particular flow, that you have a particular demand to satisfy, and the total amount of water, and so on. And when you plug this into the computer, computer kind of finds out, based on this mathematical shape of these functions, finds out the single solution which will tell you build the pipe of this diameter. The similar thing can be done when we have more than one objective function. This is so-called the multi-objective context. In this multi-objective context, you have now to trade off between different objectives. So we may look at the cost as one objective. We may look at some environmental impact as another one. We may look at the, let's say, amount of flow or the demand as a third one. And these are all kind of formal mathematical tools that give you opportunity to come up with the solutions, but in a kind of different forms. They have a value for almost every activity within the disaster management, the integrated disaster management approach, and they have a variety of forms. They can support linear functions, nonlinear functions, dynamic characteristics, stochastic, deterministic, and so on. This is an example from United States, from Houston, where this particular community was facing serious problems from the flooding coming from the small creek that was put under the ground. So what they had a underground piece of infrastructure that the water was basically going under. And the community developed around, basically not realizing that they are living in a place that may be affected by flooding. So with the larger flows exceeding the capacity of the problem started occurring. The community started majorly deteriorating. The people were moving out, selling the properties. The values were dropping down. So the city decided to put some effort in finding the potential ways to deal with the problem. And various opportunities were kind of investigated, about 8 different alternatives, like opening the creek, building the small park around, kind of creating some kind of natural setup that will allow water, high waters to flow, but also enhance the community life, and so on. They communicated directly with the community to select, how are they going to choose among these 10 different alternatives. So this is a typical multi-objective analysis problem. So you have 10 different 10 alternatives, and you have 10 different objectives. So the people were providing the input, and there were some issues like, some criteria like maximizing the flood loss prevention, to minimizing the number of relocations because you have to do something with the land in order to create the park, and so on, to minimizing the legal obstacles. And you see variety of the kind of objectives and criteria that are affecting the choice between these 10 different alternatives. You can approach this problem by collecting then the data, creating so-called the payoff matrix. These are the kind of criteria, these are alternatives, these are the inputs that can be kind of objective, subjective. If you're talking about costs, will be dollars. If you're talking about flows, will be cubic meters per second. And then applying some of these mathematical tools can help us kind of rank these alternatives. And then you see which of the alternatives is kind of providing the best trade-off among these objectives provided by the people. So this is illustrating another way of implementing the systems analysis to deal with the kind of complex water resources management and natural disaster management problems. The last two examples are dealing now with illustration how this my risk management idea can come into the place. And I want to bring out this is as a theoretical concept, and that's something relatively new. The theory of fuzzy sets is not very popular, especially not very popular in the West. I think in some Eastern countries it had a much more of the application, in spite of the fact that it was developed in Berkeley by the scientist who was originally coming from Poland. But the whole mathematical theory is based on the replacing the probabilistic concept that depends on the available data. In order to arrive at the probabilities, we need to have observation. We need to have data. To replace this concept with the kind of human input and human values or judgments that may be quantified. The quantification comes in the form of what is called the membership function, and the membership function will be something that describes what the tall man is. Okay, so the tall man for you may be 180 centimeters. Tall man for somebody else may be 185. For somebody else 175. So collecting all these inputs, we can now create the representation of the tall man. Okay, this is 180, and this is right around 200, and this is 170. So this is derived on the general kind of opinion that you collect through the interviews and the subjective inputs into the analysis, not the observation of the height of the man in the region. And similarly, we can also use this kind of fuzzy sets to illustrate the acceptable level of performance. What is acceptable level of protection from the flood? Is it, this height of the dike, or this height of the dike, or this height of the dike? So you can kind of represent using these membership functions. You can represent the state of the system. You can represent the acceptable level. And now the neat mathematical thing is, I'm not going to bother with too much mathematics, is this shaded area which provides the overlap, and that overlap is in a way nicely defining the risk or the performance of that system. So this is the concept that I kind of introduced in order to be able now, the probability is very known. We know how to come up with the frequency, with the different distribution functions, apply the different theoretical models, and then use the theoretical models to predict the values corresponding to different return periods. But through this, we can now bring actually the subjective use and the subjective uncertainties into the risk management process. And this is the picture from 1997 flood, what I was telling you about. From the plane, you were able to see this was basically where the river was, and this was like a 2,000 square kilometer. Very, very south from the city. Winnipeg is a city of 750,000 people. For Canadian conditions, pretty large. I don't know what, fifth, sixth in Canada, the size, I'm not sure. And it's protected by the floodway. What you see here is basically the artificial structure. This is the small dam. The city is here, and the river kind of goes through the city. This is south. U.S. is here, 80 kilometers down. So when the high water comes, they close the structure, and the water is diverted through this floodway around the city. At that time, the water level in the floodway was 2 centimeters below the bottom. So it was just a question of small wind or a little bit more flow on the major disaster. we estimated the potential damage within the city if the floodway failed would be in the range of $9.5 billion. This is for Canada, very large figure. So they decided to do something. Okay, I was not planning to talk about that. I wanted to tell you how we developed some kind of risk management tool for dealing with the flooding and understanding the flooding in the region using this concept and the theory of fuzzy sets. I'm sorry about all these kind of details that are not visible to you, but basically they're describing the flow chart of the process where we utilize the information to create these membership functions now in 3 dimensions to include the change in the, let's say, water level at a particular location at a particular time, and the change in the flood damage at a particular location at a particular time. And when you combine them, then you get the shape like this. And that was able then, through the calculation of that overlap that I was talking about, to give us the value of risk that we were able to map. What you see here, the city is here. This is the region. This is the city that was fully protected by the ring dike, so there is nothing happening within the city. Everything is protected. And these are the kind of flooded areas. The shades of the colors are indicating high and low risk. And what we were able now to do is, through this type of calculation that took into consideration all the subjective and objective inputs, to generate the risk map. This is the timing of the peak. We simulated now the flows of the 1997 flood, exactly May 3rd. And you can see how is the kind of risk changing with the change of the flow that goes through the system. So this was the first time that we were able to actually generate this risk map that can be of tremendous value for the managers, for, let's say, planning different options. The river is protected and communities are protected by dikes mostly. This is a very flat area. But also evacuation is being used if the flows are very high. So for example, the city gets completely closed, diked, and all the people are moved out to safety. So having this information in this particular form, now we were able better to understand the difference in this, in kind of space, and how is this changing over time, and possibly assist in this particular case, flood management process. And the last example is, some of you already heard this example, is the example where we look at the climate change, by mistake, okay. Climate change, flooding risk, and the impact of climate change caused flood risk on the municipal infrastructure in the city of London, where I live right now. So in this particular case, we were also now looking into this integrated representation of risk as a hazard and consequence combined together, where hazard was now much more sophisticated assessment of the climate change caused hazard conditions or flooding, and consequences were measured by the impact on the municipal infrastructure. The project was done for the City of London, and they indicated the type of infrastructure to be considered in this particular project. So we were focusing on buildings, transportation infrastructure like roads, bridges, flood protection infrastructure, dikes. We have a large reservoir close to the airport, and other type of emergency management infrastructure like location of hospitals, fire stations, police stations, schools that are usually used for evacuation, and so on, and the water conveyance infrastructure. So what we have done in this work, we kind of integrated now the very complex assessment of the changing conditions or changing flooding conditions due to the climate change with the set of realistic consequences that may occur in relationship to the selected infrastructure by the municipality. The way to deal with the climate change, because of the numerous issues related to uncertainty in choosing different climate models and choosing different emission scenarios, we opted to proceed with a range of potential impact by selecting the kind of upper and lower bounds of the climate change. And then we plug that into so-called the downscaling tool that brings the global information to a local scale of the watershed. This particular watershed, the city is located in the Thames River watershed. It's located at the bottom. This whole watershed is about 3,700 square kilometers. What you see is the kind of consequence of the animation of the generated precipitation patterns as a consequence of different changing climate conditions represented by these two upper and lower bound climate models. So now we had an input into our traditional analysis, hydrologic analysis that was done to convert now the precipitation into flow. These are the kind of rivers and creeks, 170 points within the city, for which we were able now to use the hydrologic model and generate the runoff or the flow. And then utilize the statistical analysis to see what is the character of the change and proceed with the impact analysis. So this is interesting. The full line is this is the probability of the flow at the exit from the city, Byron Station. Full line represents the observed history and the data, and the dashed line represents upper bound of the climate change scenario. So what you see for this particular region is that if this is representing the 100-year return period, or the probability of flow that occurs every year with the probability of 0.01, that this return period under the changing conditions is becoming much shorter, or that these type of floods may be experienced much more frequently. So up to 31, 32 years, every 31, 32 years. If you look at the magnitude, like the change that's represented by this difference is approximately 25%. So very significant, or the indication of the very significant impact of climate change on the occurrence of floods in the region and affecting the city. So we were able now to generate these probabilistic outcomes, and then to proceed with the analysis, we were focusing on something that's called regulatory flooding, and in our legislation, each community has these so-called two floodplains, 100-year and 250-year floodplains. Within the 100-year floodplain, nothing should be built. Within 250 years, with a special permit by the conservation authority or the community, you can actually build something. So now we had the upper and lower climate change scenario. We had a 100 and 250-year hydrologic scenario, and we were able to do the impact analysis. We used the hydraulic models to find out basically the inundation. What you see here is a very typical outcome, like an extent of inundation that corresponds to a particular climate and hydrologic scenario. The shade of blue represents the depth, water depth, and that was the kind of assessment of the hazard. We were able to generate 4 scenarios: climate upper and lower bound, 100-year and 250-year period. So these 4 then went into the calculation of risk by simply combining now the floodplain and the detailed information about the exposed infrastructure. What you see here is a very typical kind of GIS map that shows the location of the buildings, roads, and for each of these pieces of infrastructure you have a detailed elevation and other necessary information. Most of these also have the so-called stage damage relationships, or the economic description of the potential impact of inundation. So we were able to kind of integrate that all together to assess the risk. We introduced a couple of innovations in this process. Beside the hazard, that was for the first time done under the changing climatic conditions, we were also looking into the consequences in a different ways. Not only how much the particular piece of infrastructure will be under the water and how deep the water will be there, but also what is the role of this piece of infrastructure. Is there a function that this infrastructure is kind of performing, and is this function being affected or not. So loss of function, loss of equipment, loss of structure, they're all kind of aspects that were integrated in this risk formula, and they were able to provide us with so-called risk index that kind of puts together now the different kinds of infrastructure, kinds that we were looking at, and different kinds of impact, and the hazard was coming through these four different scenarios. The point is that in this, we were also able now to use the objective data, the observations, the inundation, the location of the building, and the age and everything else. But we were also able, because this is an infrastructure, to talk to the engineers and learn in what state the infrastructure is. So it's not only is the water going to affect the bridge, but also when was the last time that the bridge was maintained, in what state is the kind of bridge, how the piers are being protected or not protected, and so on. So this is where we utilize, this is a typical kind of economic input depth versus damage. We were able to utilize this fuzzy set idea by talking to the people to get assessment of the state of the system due to the maintenance, age, type of material, exposure, and so on. And that was all kind of integrated. So all what we needed to do is to find a way how to communicate this message, because this whole analysis involved approximately 4,000 and so many pieces of infrastructure that we considered, and communicated that to the decision makers required finding appropriate presentation format. So we opted for something like this. These are the boundaries of the cities. What you see is different level of risk represented in shades of red for these uneven spatial units that are called, in our case, dissemination units. Dissemination units are representing the areas with approximately same population density. So you see that, for example, outskirts of the city, they're larger. Within the downtown, they are smaller because of the density of the population. And when we now look at each of the units, we were able to locate all the pieces of infrastructure at the risk and kind of assign that level of risk to the particular spatial unit. And this was very well accepted by the city and the politicians in the city, as well as the kind of engineers, because they were able to kind of see the spatial distribution of the risk. They were able to see the contribution in the extent of the risk. And the first question I got from the chief engineer was, how much money is this? Okay, this was representing one particular climate change lower bound scenario in one return period. And our calculations, back of the envelope calculations that was a relatively fast done for the most extreme kind of flooding condition, was approximately $800 million. $800 million is extremely large amount of money for the city of 350,000 people. There is no way that city can deal with that kind of price tag. So elimination, what I was telling you earlier, the elimination of risk is out of question. You cannot, turn everything into white. But now they had a pretty good sense where are the kind of critical points, and they were able to possibly prioritize the investment and the way how they're going to deal with this risk by focusing on these areas where you can reduce the higher level of risk in a most efficient way. So it was very easy for them, like, oh, okay, this is a very dark area, very high risk, click on that particular area, see what it is. These two examples are very interesting. We have 6 wastewater treatment plants. And they're all in the floodplain. Extremely expensive pieces of infrastructure. If they get flooded, you have a mechanical, electrical equipment inside. Obviously, they cannot function during the period of flooding and so on. So very large risk or the exposure. This was another interesting example. This is an Oxford Street, relatively kind of downtown area, but we have an old railway going through. And there was a culvert under the railway here that obviously didn't have sufficient capacity for the higher flows that climate change may cause, and that may affect this. This is all the residential neighborhoods. So it was a very interesting reaction. They immediately, when I was making presentation, the politicians immediately jumped, oh, we should be talking. Railway in Canada is the federal responsibility. So for them, this was immediately the problem. They needed to transfer to somebody else to talk to the federal government to see how they can, deal with that, because city is obviously responsible for the population and the impact on the population, but cannot do or change that. So this was a way of doing a number of things. We were able to bring the climate change and the change of the hazard conditions. We were able to bring the objective and subjective kind of risks through this particular risk formula, and we were able to kind of communicate now the information onto the decision makers that they can make some important decisions. This is the kind of end of my presentation. Before I finish, I just would like to leave you with 2-3 very important messages. Sorry, the messages are in the Canadian context, but I think they have value for you in Taiwan too. The first message is coming from the briefing that the Minister of Public Safety, we have a Federal Ministry of Public Safety and Emergency Management. And for the first time last year, in the briefing to the Prime Minister, we don't have a president, we have a Prime Minister, the Minister of Public Safety pointed out that the rising cost of natural disasters and the financial burden on the country is so high that it starts to represent the biggest public safety risk. This was the first time in the history of the country that basically natural disasters were identified as the main source of the potential public safety risk. The reason for this was that in 2013 we had 2 very large flood events. One hit the city of Calgary, central Alberta, generated $6.5 billion damage. And another one was a 2-hour rainfall event that hit city of Toronto and generated 220 millimeters of rain over 2 hours and paralyzed a portion of the city. $1.7 billion of damage. So these 2 figures in 1 year were affecting the Canadian budget. Canada belongs to a developed country, and you can realize, what the disaster events of this magnitude can do to countries with a lower economic capacity to deal with that. But for the first time, we're seeing now that natural disasters are coming very high on the agenda. Unfortunately, the same ministry didn't devote the equal proportion of the budget, to dealing with the natural disasters, but that's another story. The second message is related to climate change, and I'm quoting here the Professor Black from Harvard Business School, who was talking about use of this term. In English, we use the believe in climate change. And there is a huge public, debate on, who believes, who doesn't believe. And he's kind of questioning here, should we, are we talking here, how can you use the term believe? There is nothing, to deal with the religious, so this is not a religious question, and there is nothing to deal with the belief. We are talking about changing conditions, and basically the question of decision making under the high level of uncertainty, and that's what I was trying to present through the lecture also as my kind of point of view. So in dealing with the climate change, we are not dealing with the beliefs, we are dealing with the changing physical conditions, and these conditions are obviously subject to some level of uncertainty that comes from the knowledge, from the data, and available information. But we will need to continue making decisions under that uncertainty. And the final message, I'm not completely sure how relevant is this for Taiwan, but for us, for Canada, is very, very essential. We do not have, for example, flood insurance in Canada. And insurance is representing basically mobilization of the private funds, private money, that can be combined together with the public funds and public money to deal with the natural disasters and the consequences of natural disasters. And the main reason the insurers were permanently rejecting to provide this type of insurance was Canada is a very large country, very small population, therefore it will be very expensive to sell this. And what we have done is, that there are some ways and there's some, I think, models that can be explored to integrate the public and private funds, to deal with the disasters. There are some examples from UK and some other countries. There is an example from the US, which is not an extremely good example, where the insurance is being provided through the kind of federal government that's selling it. But the point is that we need to look at for alternative models how to deal with the natural disaster. The cost is becoming so high that the governments, including my government, are becoming unable to kind of meet or to pay these bills. So we need to find a way how to integrate, I think, the private. So their models, their ways of kind of not in or basically providing the rules and suggestions how to avoid building in the prone areas, disaster-prone areas, to find a way how to increase the coverage that all different all different disasters can generate. Finding the kind of ways how to build this partnership between the industry, governments, and private homeowners, and deal with the future disasters. So what I tried here, this is your Morocco in 2009. What I tried here is to illustrate, the complexity of the disaster management problem and really the need to look at the problem in a different ways. I offered you with the two kind of views and two different approaches. One is based on the systems view, systems thinking, systems analysis, where we look at the problem in a broader sense as a set of components that are working together. And another one is a look at the risk or risk management as a mechanism for adapting to changing conditions. And within this risk management, considering both objective and subjective aspects of this in explicit form. Thank you very much for your time, attention. It's a long speech. Tony was asking. So I'll be very happy to answer some questions or hear the comments or. Go ahead.
Hi, my name is Shu Harling. Thank you so much for sharing your experience. And it seems to me, I'm very curious about your problem model, and especially you use that use the model to assess a lot of the loss of disaster loss and a lot of things. And I'm just wondering about whether your model can be used to assess the infrastructure function. I mean, whenever we put some infrastructure on a certain area, and according to your model, they can even to reduce in the flooding area, or even you can coverage the losses of the disaster, and so on.
Which model are you talking about?
Huh?
Which model are you talking? The one in the Red River?
The river, and that you have a flooding model and the.
Yeah, but both were dealing with floods. The last one in the city and the one in the city one. Yeah. Okay. Actually, the answer to both models is that yes, the models can be used, and this is the main intention. Can be used to kind of assess the impact on the different conditions. So, if potential options are to introduce some protection infrastructure, you can plug in that into the model and see the consequence to on the overall risk distribution in space and time. For the city model, the last one example I presented, now the city proceeded after we completed this study with 8 smaller studies that are focusing on the very detailed analysis of each of the creeks and basically assessment of the options. So they're asking, they're working with the consultants and consulting companies, and they're asking for the different solutions, either bike or a different way of protection, and they are using our kind of risk modeling as the mechanism to assess the impacts of these different potential solutions, and the city will be deciding how to proceed. So the objective is to reduce that risk from flooding. There are different ways: structural, non-structural. I know that they are doing some work for the wastewater treatment plants. Very simple kind of protection measures. They're moving the mechanical and electrical equipment to the higher kind of elevation within the plants, and they are providing some small modifications that will simply increase or reduce the potential risk to lack of action. For the dikes throughout the city, they're doing now very detailed review to find out, is the level of protection, design level of protection still maintained, or what will be the change under the changing conditions. So they will be deciding, are they going to upgrade some dikes? Are they going to keep some dikes as they are? Depending on the impact, depending what's behind the dike, what is the kind of level of risk that you can reduce by introducing the measure. So they are using the model for particularly that purpose of assessing the different structural and non-structural options.
That would be very interesting about it. They can use it for the, especially for the policy maker. And I'm just wondering, and also that you mentioned about the climate change that may increase the frequencies and the intensity in the future for interconnect. I'm wondering that how long, I mean, what data period that you used.
Okay. We used a very traditional way because the main input was from the global climate models that were then downscaled within this range of upper and lower bound to local conditions. We used very traditional output that the global models are providing, basically simulations for the next 100 years.
100 years?
100 years of climate data. But then when we developed the downscaling tool to bring that to a local level, we used the statistical downscaling tool. It's called the weather generator. It's based on a so-called K nearest neighbors algorithm. And with this tool, we can generate as long sequence of the future precipitation events as you want, based on this climate input. So what we were doing, what you have seen as animation, was about 320 years of the precipitation events. And we did that in order to develop these probability distribution functions. So I wanted to have a very long sequence so that we have a 100-year representation with, a supported number of data points.
Okay, but in addition, I'm just wondering about things you talk about long time, that 100 years later, but especially for the AR5, they emphasize about how about the near future change. So have you ever did some study about that?
Okay, you have to be very careful with your language. when we say 100 years of simulation, that doesn't mean that this change will be happening, 100 years from now. Okay, so these are the climate models are physical models. They are representing the interaction, so the processes in the atmosphere, interaction between the atmosphere and the solar surface, and the ocean surface, and 32 layers within the ocean. So trying to capture the change within this physical system over the long period of time. And that's why we use this 100 years of simulation. But when we use this information, we go into like this downscaling and create a tool, then we are basically switching into the probabilistic representation. Okay, I can generate now the sequence of input, I can find out the probability, and then we work with this kind of probability. So it's not anymore 100-year flood. It's actually, you have to understand that I'm failing students for this. The 100-year flood means the potential of flooding every year with a probability of 0.01. Okay, so we can have in the same year, and we did last year in Canada, we had 200-year floods in the same year.
In recent period?
100 years. Okay. That's what I'm saying. So this is the probability.
Other questions? Yeah. Well, thank you very much for the presentation. It's real nice, especially with case history. That's very interesting. Very good. I have a question on the system approaches you seem to involve a lot of things you talk about. Have to talk to people, social or psychological. How many people you talk to? What's the data quality? I mean, you can do the put it in the box and come up some numbers, but how good is the data? And how many people you need to talk to?
Everything depends on the kind of application. I don't think there is a general answer to that question. But like when we were developing this evacuation model, we actually conducted, or our colleagues in social sciences conducted a survey of all the municipalities flooded in 1997. So it included 8 municipalities on the Canadian side of the border, and I'm not completely, don't remember the exact number. There were approximately 400 or 500 families, or 2,000 to 3,000 people involved in providing that information. In the work on this, I didn't show the example of this coastal cities at risk. We have also the social health economic and the kind of physical aspects of this integrated together. And what we are doing is we are doing very similar thing. We are kind of conducting, or our colleagues in social science, they are collecting the information within the cities. They are using their own, methods of social sciences. What is the representative sample? What is the quality of the data? And what I'm doing, I'm kind of putting that together into system tool to assess the risk or the resilience. It depends. Everything I think depends on the kind of focus on the problem as well as on also what is kind of the main. City of Manila and Vancouver, two completely different approaches. In Vancouver, we have 2 million people. The concentration in two areas which are low-lying. In Manila, they have between 10 and 30 million people. They don't know exactly. During the day, it's probably closer to 30. During the night, it's 10, because of people moving, and nobody knows where these people are. So for them, kind of finding and making that assessment is much more difficult. But they are also doing, their social scientists are doing the studies. They have kind of sample communities and special methods how they assess it.
Quite interesting. The model you talked about, and also the decision process you talked about, you put in the subjective input. That's very interesting. I have not seen anything like this before, so this is quite new. And the question I was wondering is that in this approach, when especially this so-called social computing age, this subjective value type of thing could be affected easily by filters, things like that.
By sharing information
right,
in
yeah.
different ways. Yeah.
And that aspect, is that being considered?
Not so much. I mean, in the evacuation case, it was. You see, we actually had a set of questions that were posed to each family that was evacuated. What is the most acceptable way, or receiving that information? So that would be going into that. Into kind of in the coastal cities project, we are not dealing so much with the evacuation or the emergency response. We are dealing with the long-term climate change impact. So our focus is in both in the social, economic, and physical side to look at that longer term kind of change. So how is the community changing? How it's growing? What are the characteristics of the change? Are the people focusing focusing on a particular area? Is this where the density is becoming higher or not? We have a very large mix of different cultural backgrounds. Vancouver is exposed to a lot of Asian population, and they tend to stay together. So the density is increasing in the same area, whereas the other people are moving. So we are trying to capture this type of changes, social kind of changes and trends that will affect the population density, and therefore the kind of impact on them by those long-term climate changing conditions. So everything depends on basically on the problem, and then you kind of structure the way how you bring this information. But the information sharing is very important. It is important. It's in every aspect of disaster management. I think it's really becoming crucial. And nowadays we have this kind of very shorter and shorter time where the information is being kind of communicated faster and faster. It was interesting. I had the opportunity to go to Japan after the earthquake and Fukushima. And they started talking, the Japanese were starting to develop a lot of tools based on available technology, like mobile phones, so that information about the disaster you can receive on your phone, and you know exactly where you are and what to do and so on. And they realized during the disaster the complete network was out of use. And now they're kind of saying, yes, the technology is available, but the technology may be affected. So if you rely so much on that technology to disseminate the information, you may not, you may not succeed. So you always, you have to consider the types of disasters. You have to consider, the kind of level of technology available and the potential impact on the technology.
Okay, I think. Maybe afterwards. Okay, after this. Let's thank the moderator again. Very nice.
Thank you.
Wonderful lecture.
Yeah. Thank you.
Okay.
Yeah.
Thank you.
Thank you very much. Actually, these frameworks activate others and matching frameworks emphasize feedback, interaction among workshops. But however, they are more like a conceptual one rather than just operational one. So I'm just wondering, do you really major feedback for the interaction with the model?
Supporting the kind of operational activities you try to kind of think that, they are used for either planning or, developing some legislation or so on that you use. Okay, the key message is that I think we have a tools, we have ability to capture all these different things and put them in a kind of model form so that, models can use them after. That's the fact.
You want to sit down.
I'm okay. I'm okay.
When do you want to go to dinner?
You just said.
You need to go back to your room a little bit?
Do you want to go back? Do you think it's early for you?
Yeah, it's still early right now. It's just 4. What about 5:30?
5:30? Okay. You want to sit back here?
Okay, if you come here, and you can be at 5.
Okay. Yeah, 5:30. And we don't need to be formal.
No.
Okay, thank you.
Okay.
Do you have another question? Yeah, go ahead.
I also noticed that your show is the same program. Did you were that developed that program or?
Stella is the tool that you buy. Okay, they are using nowadays more actually dancing. These are very powerful graphic object-oriented programming tools that are tailored for system analysis simulation. So what we have done, we kind of adopted and teaching also, how to use it, how to do the system analysis modeling. And these tools, they're very inexpensive, the Vincent was $850 or something like that. Very inexpensive, very powerful, very easy to program. So,
It's at 5 o'clock. It's at 5 o'clock, okay?
I will try to find a
I have in both texts, I have actually the Chinese one also. I have a whole chapter on systems analysis simulation. I also have a set of examples, and on the CD, you get the CD with the book. You actually get the student version of the software for free, like what so you can try a little bit with it. The main benefit of the system analysis is that you can with the same principles, you can model the social system as the physical system. Like how the people communicate, behave, you see what you have done with it. So this is why I'm strongly recommending this approach, because you have a lot of opportunities to kind of look at different aspects, different sectors, how these sectors interact and so on.
Yeah, that sounds wonderful. I will try.
Yeah. If you need anything, you can contact me and no problem and share the information basically.
I will, definitely. My name is Ilan Zin, and I'm a postdoctor here in Academia Sinica.
Oh,
So
Yeah.
I will email you and then
No problem.
shall I write
Yeah.
down my notes for you or?
Yeah, you send me an email. That's easy.
Okay.
Yeah, you send me an email and then I know.
Thank you very much. Thanks.
You're welcome.
I'm Huang Lee from
thank you.
Academia University and actually participating in one of the sort projects here funded by the Sinica, which is on the climate change impact on very similar to what you mentioned in one of your slides on the climate, water, food, energy, and also we integrated the dynamic population, demographic composition change for Taiwan, and for the whole for the whole nation, not just for certain city or.
Yeah, we did that too. Also, I didn't talk about that, but in that particular project, we have a model that actually represents the global change, so like the whole planet, and we have a regional version of the model that actually models the whole Canada. So we are looking into climate and population as the main drivers. We look at all sectors related to water quantity, demand, and quality as transporters, and then impacts on the kind of food production, economy, energy production, and energy use. So the model is called ANEMI, and if you go to
your website?
Yeah, to the website and the research lab, you will find actually the model. We are distributing the model. You'll find the manuals and everything else. And if you have more questions, you just send us an email. Yeah. And we have already 3 papers published out of that. So besides on the web, you will find the manuals and the detailed description. But if you want to just see the papers, also the references are there.
Yeah. Thank you very much for your lecture today. The disaster one is also the one that I'm going to do for the coming year. I applied for I wrote a proposal to do some research on disaster impact assessment, particularly from the economic perspective.
We have in this coastal cities project, we have a very detailed economic component, and it's also system dynamic. And in that work, ANEMI modeling, we also worked with the 3 economists, and we embedded very detailed economic optimization model within the simulation model. So the economists like to look at the price and impact and price on the availability, and they like to optimize the price, like for energy generation from different sources and things like that. So this is all done, and through the simulation, then you communicate this to other sectors, and you see how these interactions are occurring or feedbacks.
One of the questions I have for your presentation earlier is that you mentioned about that there's a price variable and the money value for every kind of risk. Right?
Yeah.
How do you get that information? Like for example, for city scale.
In our case, this type of information is being collected by the regional government province.
Okay.
So they have to provide the so-called depth damage information. So what they do the kind of survey assessment of the properties, and then average value of the property, and then they develop like we have a typical 2-story home or a single-story home, and you have an average price of the home. So if it's a half meter under the water, if it's when it's fully damaged, when it's partially damaged. So they are developing these relationships, and they provide that to everyone who needs that, either for research or for economic studies and details of that.
So the government already got all this information.
Yeah. They are not very good because they should be updated. This information is changing because the value, average value. This is a kind of market forces, and so this is really you have to update that very often. They're not doing. They're complaining they don't have enough time, they don't have enough money, and so on. But that's how it goes.
Right, but there's a problem here in Taiwan because for the local government, they may not have so much budget to do this kind of survey or inventory of all the